Good morning, good afternoon, good evening, depending on where you are. My name is Gerald Verbeek, and I'll be the moderator for this It's Money webinar. We will start at the top of the hour, but I want to welcome those of you that have already logged on. And I would appreciate if you could let us know that the sound is loud and clear. That will be a great help. Once again, I want to welcome all of you that have already logged on to this It's Money webinar for April of 2022. We will start at the top of the hour in about 6 minutes. Good morning, good afternoon, good evening, depending on where you are, and welcome to this edition of It's Money webinar. We will start at the top of the hour, but I appreciate all of you that have already logged on early, and I would appreciate if somebody can just use the chat box or the Q&A box to let us know that the sound is loud and clear. That would be great help. Thank you for that response, and at least everything is okay so that we can get started without any technical problems in about 4 minutes. Once again, I want to welcome all of you that have logged on to this It's Money webinar. The actual webinar will start in about 2 minutes. Good morning, good afternoon, good evening. Welcome to this edition of It's Money webinar for April 2022. My name is Gerald Verbeek. I'm a member of the Testing and Evaluation Committee, and this webinar is produced by that committee, and I really appreciate that you have logged on for this edition of the webinar. Before we actually get started, a few housekeeping notes that you can see on the next slide as well. During the webinar, you are going to be muted. And if you have any questions, either during a presentation or after a presentation, please use the Q&A box that you can find on the bottom of your screen so that I can then communicate the questions to the presenters. You can also use the chat box. Either way, I will be monitoring both of them. There will be a short Q&A, time permitting, after each presentation, because we will keep 30 minutes for each presentation. And then after the 3 presentations, there will be another half an hour of Q&A. So that's kind of the housekeeping notes. For this edition of It's webinar, we have 3 very interesting presentations, and it's really a pleasure to do this. Right now, I'm in the Netherlands. We have a speaker from the Netherlands. We have a speaker from the UK. We have a speaker from North America. So it's truly an international event today, illustrating that wherever you are, whichever part of the world you are, increased testing does save money, because as you will hear, one of the presentations will actually take us to Africa for a project there. So a truly international edition of It's Money with some very interesting presentations. And the first one is by Patrick IJnsen. He is with the Van Hecht Group in the Netherlands, and he will give us a case study about a load test on a railroad underpass in the Netherlands. Patrick, the floor is yours. We don't hear you, Patrick. You are mute. Well, maybe we do have some technical problems. What may be best, Carol, if you could just move the slides forward to Dustin's presentation. then we will let okay. While we try to sort out these problems with Patrick in the Netherlands, let's go back to the United States with Dustin Walkenhorst. He is with Keller North America, who's going to talk about an expansion of a shopping mall in Florida. Dustin, the floor is yours.
Great, thank you, Gerald. As you mentioned, my name is Dustin Walkenhorst with Keller North America. I'm going to take a little bit of time and talk about some micropile load testing we did for a shopping mall. Here's called Ball Harbor Shops, very upscale, large shopping mall in the Miami area. So this project was one where we were expanding this building. We were taking some time going in between a lot of tide access, low headroom area to install some micropiles to add some expansions and allow for some additional loading to this project. The project consisted of about 120 micropiles spread out, like I said, mixed with low headroom, tide access, underneath tide areas inside the building. They were spread out all over, but this was done to allow for the expansion of the mall. We went into this project with a plan. We had micropiles drilled down to the top of the limestone layer. We were going to drill a 15-foot rock socket into that limestone. At that point, we were going to grout up, come to the surface, drop in some bar, and prepare to connect to the foundation. As all plans go, they change as we went along. We drilled down. We can show here the geotech report, one of the example boring logs with our micropile next to it. We drilled down to the limestone. We began to drill our rock socket, got down about 13 feet and we lost return. We filled that micropile up with grout, and the grout take was about 400% over the theoretical. This was for the load test pile that we were installing to be prepared. So we filled that one up, we moved over, attempted another one, we drilled deeper, took the casing down deeper with the theory that we would get down, drill past whatever was losing our return. But once again, we lost our return, filled that up with a much higher theoretical volume than expected, about 500% on this one. So we developed a plan. This is a technique we've done many times. We drilled down on that same pile, the deeper one, drilled down and pumped a very low mobility compaction grout to fill in whatever void, fissures, small things were down there. Miami is a karstic limestone area known for fissures, small voids, different things like that tend to suck up grout. We were not expecting it on this one, but we came in with a plan. So we pumped in our low mobility compaction grout to reduce the grout overages. And then the next day we came back in and we drilled that pile, pumped up fine. So that was a solution that we could have gone with, but at that point we called a timeout. We got with the geotech team, the structural and the general contractor and the client. We talked them through, told them, hey, this is what we're seeing. It's unexpected. These are our options. We can do this compaction grouting. Drilling deeper is an option. We have multiple options we could do here to still get you the performance you need as far as loads and settlement. Or the other option is we can do some additional testing. So as mentioned before, the borings had no sign of loss of returns when the geotech did their report. There were no voids or anything visible in the borings. But as we all know in geotechnical engineering, expect the unexpected. So we worked with the client and the engineering team. We provided the client costs for doing the compaction grout technique, which mainly involved additional grouting and additional time, considering we had to drill each pile, compaction grout, let that set up, come back in and do it again another day. So that lengthened the schedule and increased the cost for grout and labor at that point. So we provided with the client with these potential cost overages. We show here, worst case, or at the time of bidding of the original cost of the piles was about $700,000. The cost of drilling the longer piles was an extra $100,000. Potential worst case, and the cost of grout overages, these are all estimated from that load test, but the potential worst case was almost $1 million of additional cost. We talked those things through with everyone. Talked to them about what the added time to the schedule would be. This was a very tight schedule. They needed to get these remediations done so they could open back up portions of the building, open back parking area. Parking in South Florida is very tight. So any loss of parking is a big hit to any business down there. So we talked these things through with them. And eventually we came to an alternate solution that we provided to them was to install a new pile that had a shorter bond length that would keep us above these small fissures and things that were sucking up the grout. And that cost was roughly $50,000 to run that cost. We told them we would do this cost with a shorter pile, and based on our drill logs and what we were seeing, we wouldn't lose return. We'd be able to get a good pile in there. So let's test this and see if we can get the load that you need with a shorter pile. So we got approval from everybody. Everyone felt good about this plan. So we went in, installed our test pile, and performed the test. So we pushed it to 200%, which are typical, and performed great. Nice linear curve there. Rebound was good, and we were less than a 1/4 inch of deflection. Our goal was less than an inch of settlement at design load, and we were well within there. The geotech said, hey, I'd really like to know what kind of load we can get out of this. So we said we'll push it to the capacity of our test setup. So we took it to 320 kips, almost 300% of the design load, and it performed great to the 200%. Started to settle a little more, but we felt like we had a good ultimate capacity on this pile at that time. So that was presented to the geotech. It was presented to structural. Everyone looked. We had a lot of meetings and talk throughs, but everyone felt good with that outcome at that point. We strain gauged these piles as well, so we could see where our load transfer was occurring, and showed that with this shorter pile, we still had the 2 times factor that we needed for the load on these piles. So by doing this additional load testing of this pile, it costs, $50,000. The potential additional costs that we were looking at was $1 million for worst case ideas. So with this plan, with additional testing that we put into this project, we showed, and the client felt really great about this additional cost savings that we had to the project, provided the performance they still needed, and avoided additional costs from unexpected ground surface conditions. that's all I have on this one. Give a little bit of time for questions, or as was mentioned earlier, there's will be additional time for questions at the end of the presentations here.
Thanks, Dustin, for a great illustration of increased testing saves money. Looking back at this project, would you have approached it still differently to avoid with these unexpected soil conditions? Is it something that if you now approach a project in Florida, that you are a little bit more careful up front? What was the longer term learning point of this project?
Yeah, that's a good question. We've done thousands and thousands of micropiles here in Florida, and the majority of them, the geotech, the boring report shows if there's going to be concerns. We kind of know the areas where we've seen large voids or worse karstic areas. This one, we did not expect that. We've done a lot of them in the Miami area. The Miami area is not overly known for that, more the central Florida area is that. But I think what we've learned from this one and other ones is the ability to, like you said, to come in with a plan for additional testing is a good one, but also the compaction grouting was a lesson learned that we've had. It's a solution. If we can't get shorter piles or get around those voided areas with load testing, we know now through that one, the compaction grouting is a potential option. Can be an expensive one, but it's a potential solution that we've used.
Two other questions that have come in. First one is, was the pile group settlement considered given the load test was on an individual pile?
Yeah, it was considered. We had many conversations with the geotech team. We ran some numbers there as well, and in the end, we all felt that this was not a large void, but small fissures or small areas that would not create for deep settlement from the group settlement there. So it was considered, and it was analyzed as a team with the geotech. So we all thought that through and brought it up, but in the end, through analysis and additional calculations, we felt good about that, and everything worked out well for this project.
Okay. You said it's you spent $50,000, and the alternative would have been spending about $100 or what is it, $1 million more, I think it was.
Yeah.
Was the additional cost based on a lump sum, or how did you come up with that number? Is one of the questions that came in.
Yeah, I mean, it was kind of a difficult one to do. All we'd done is tried to install a load test pile, right? So we had one pile to try to extrapolate to the rest of the 120 production piles. But that $1 million, as mentioned in the presentation, is a worst case if we had to do the same technique we did for that test pile, where with drilling deeper and pumping compaction grout, coming back in the next day and re-drilling. We took the additional costs on that one and extrapolated it to the 120 production. So we're trying to give the client the worst case, knowing that it probably wasn't the case for all of them, but wanted them to be very transparent with them to see what the potentials could be.
Yep.
To see that.
Okay. Another question that came in, was there a change in the total number of piles based on the higher load test?
Where we could, there was. Local building codes limit the reduction of piles and isolated caps to at least a minimum of 3, unless there's grade beams. So most of these ones were 3 PCs in the shear caps, where there were enough piles there to still meet the code. We did do a small reduction there based on that higher load that we did with the overload. So yeah, that was definitely a benefit and some cost savings there that I didn't display, but could have been shown in that same number as well.
Right. Last question that we have for now, and then we'll go to the next presentation. When drilling the test piles, how did you know that you penetrated the pervious limestone? Was it based on drilling characteristics? Was it based on something else? How did you figure it out?
Yeah, so it was based on the drill logs, what the driller noticed. So once they hit that pervious limestone, typically when we're drilling, we'll see our returns coming back to the surface. We externally flushed these casings. So as we're drilling around the casing, the spoils are coming up around. Once we hit that pervious limestone, we lost our return. So we couldn't get those spoils back up to the surface. So we knew there was something down there that was taking that spoil and taking the grout out. So, and we were able to pinpoint where that happened with these multiple attempts at drilling this pile. So we knew exactly what depth we had there. And after we came to this shorter pile, those additional 120 production piles, we never hit that pervious or porous limestone.
Okay.
Piles.
Thank you very much once again for the very interesting presentation. We'll leave the remaining questions for the Q&A part after that.
Thank you.
The next presentation will stick to the sort of the order that we originally envisaged, that after Dustin, Devon would give his presentation. But once Patrick will give his presentation, you will understand why I put Patrick's and Dustin's presentation together, because in both cases it was kind of an unexpected situation that had to be resolved, and then was resolved very efficiently. But first, we now go to somebody in the UK who's going to give a presentation about a project in South Africa. Devon, the floor is yours.
Okay, thank you very much, Gerald. I hope you can all hear me, and good day to everyone in attendance. I want to start off by congratulating Dustin on a great presentation. Today, I'm going to talk about a project that I've been associated with for over 12 years, and believe it or not, one that I'm still working on. By way of background, in 2012, I was invited out to South Africa to participate in a series of meetings with an asset owner, the owner of a dam. And the objective of those meetings was to try to convince the asset owner of the merits of using post-tension rock anchors to strengthen their dam, which was going to be raised for increased water supply purposes. Now, after about 2 years of dialogue, the decision was made to use the anchors. And then in 2015, the project actually started. Now, I worked on that project for about 3 years as the lead anchor consultant. And then in 2018, due to procurement challenges and other non-engineering issues, the project was actually stopped for a period of 4 years. And then in January of this year, it started up again and is due to be completed at the latter end of this year. So hence my 12-year association with the project, which is quite unusual. Now, before the project was actually stopped, all 83 of the scheduled rock anchors were actually installed, but only 73 of them were stressed, tested, and locked off. So that means that the current task I have to deal with is to stress, test, and lock off the remaining 10 anchors, and also instrument them with special hydraulic load cells. So that gives you a brief background to where this is all coming from. Now, the reason I've selected this particular case study is that in my 30+ years career, this project in my mind stands out as one of the best examples showing that when an asset owner commits to an adequate program of geotechnical testing prior to the start of the main works, there can be substantial benefits for the project in terms of reduced costs and reduced program time and mitigation of risks. And hopefully this is what I aim to illustrate throughout the presentation. Unlike Dustin, I'm not going to actually quantify any cost savings. I'll do it in a qualitative sense because this is a live project and it's still subject to claims of variations. So hopefully that gives you the starting point where we're coming from. And we're going to primarily focus on this concept of investigation test carried out prior to the main contract. So let me just, hopefully my screen is live. Right, so the way I've structured this presentation, as I always do, is really start off with some very brief fundamentals. And that's really looking at defining terminology, because we're from different parts of the world, and looking at the basic concept of what a grouted anchor is. Then I'll give a brief description of the project. I'll talk about the investigation tests, the scope, the objectives, and the results of those tests. And really then move on to showing how the results of that testing was used to optimize the design of the anchor itself. And from optimizing the design of the anchor, how we reduce the costs incurred in the waterproof grouting, which is a concept I'll explain later on. We'll then finish everything off with some closing remarks. So that's the basic structure of how the talk is going to be taking place. So, some fundamentals. Most of us will know this already, but I'm not going to assume anything. This figure is taken from the execution code EN 1537, which is part of the suite of Eurocodes that we use. Typically, I'm going to be talking about the anchor head, which is a part of the anchor that usually you can see, not in every case, because sometimes they're buried, but usually you can see the anchor head, and that's a part of the anchor that's attached to the structure itself. I'm going to be referring to the free anchor length, which is a part of the anchor which connects the head and transfers loads from the anchor head through the ground to the fixed anchor, which is fully bonded to the ground. The free anchor length is actually decoupled from the surrounding grout. Now, it's that fixed anchor which is of particular interest to this talk, because that's a part of the design that the initial testing allowed us to optimize, make a lot shorter than originally envisaged, and that resulted in substantial cost savings in terms of the waterproof grouting and other concepts that I'll talk about later on. So moving on to the basic concept now. At the lower end of the scale, we've all heard of rock bolts, which is a particular form of anchor in that it does have a head, a free length, and a fixed length in certain types of rock bolts, typically 6 meters long, with working loads of up to 10 tons or 100 kilonewtons. And that's the lower end of the scale. At the other end of the scale, we have the dam stabilization anchors. And in any water retaining structure, the objective is to drill as few holes in that structure as possible. And that's why anchors in dams got very, very big. And typically we can go up to 130 meters long, with working loads of up to 17,000 kilonewtons. So these are massive systems. And it's really this part of the scale of anchor technology that I'm going to be focusing on primarily today. So we're going to be talking about the raising of Hazelmere Dam. Now, this dam is located on the east coast of South Africa, near the city of Durban. Here you have Pretoria, Johannesburg, Cape Town, Port Elizabeth, all the main sort of key areas that most of us will know about already, but we're located on the east coast near Durban. The dam itself is located on the Umhloti River in the KwaZulu-Natal region of South Africa, about 5 kilometers from the town of Verulam. It's a conventional concrete gravity dam, and it was completed in 1976. Key dimensions that the dam is 478 meters long and 47 meters high. Certainly not a massive dam by world standards, but in terms of the particular location, it was logistically a very, very important structure. More importantly, the dam was going to be raised by an unprecedented 7 meters, something that has never been taken on in this region of South Africa. Now, I've chosen this drone shot, which is looking upstream of the dam, and it shows it in its original state before any work was done on it. And I want you to focus on this particular shot, because as I go through the presentation, I'm going to show you progressively how the work's developed by referring back to shots taken from this angle, so you can get a sense of perspective. So key features of the construction work that was carried out for this raising. The first part of things is that investigations prior to the works had showed that the grout curtain had been compromised beneath the dam. And for those of you who don't know, the grout curtain is a wall of grout constructed beneath the superstructure of the dam, and it prevents percolation of water from the storage reservoir through, which can undermine the stability of the structure. So that grout curtain had to be restored, and that was one feature of the construction. The second feature of the construction was the construction of what we call a piano key weir, PKW. And it's a special configuration that is constructed in the spillway of the tunnel and allows us to not use things like radial gates, which are high maintenance items. This particular configuration increases the hydraulic efficiency of the spillway, and in fact increases the effective length of the spillway by a factor of 6. What happened was, even though the dam was going to be increased in height by 7 meters, we had to demolish 3 meters of the original spillway in order to construct this PKW. So by making the overall PKW 10 meters, it actually became the highest PKW ever constructed in the world. So that's something to note. And finally, the third part of the construction was the installation of the rock anchors for overall stability to prevent sliding and overturning of the dam. I mentioned at the outset, 83 ultra high capacity anchors were installed with test loads of up to 19,000 kilonewtons. This equals the highest capacity ever installed. The drill holes were typically 355 millimeters, and the overall length about 90 meters. So these are substantially large systems, equaling the largest in the world. And even though we're working in South Africa, the design engineers opted to use a British standard code of practice, BS 8081 1989, to govern the design, construction, and testing of the anchors. That code of practice has since been updated to a 2015 version. So, a brief comment on the site geology. The dam is founded on a material called jointed quartzitic sandstone, and all I'm illustrating here is some core recoveries, which shows the classification of the underlying stratum in terms of a fractured zone and what we termed a more competent zone. But the important thing here is that this is a banded stratum, and the fixed anchors, the most important part that is going to generate the resistance of the anchors, was actually located in the fractured zone. So we had to do special treatment to those boreholes to make sure that the grout that we're using to generate that resistance actually stayed in the borehole. And I'll come to that later on. So primarily we're focusing on the investigation test program, which amounts to the largest capacity sacrificial test anchor program in the world. This slide, again, I'm taking the drone shot from that angle I referred to earlier on, really shows the dam with the original spillway completely demolished, and they're now starting the construction of the PKW in the spillway location. But what's important here is that we elected to install 4 sacrificial anchors, 3 in the spillway, in the stilling basin, in the spillway location, 1 on the left flank as you're looking downstream, and then a 5th test anchor, which is what we call a dress rehearsal anchor, because it was fully configured like the production anchors straight through the non-overspilled crest of the dam. And the idea of that was so that the contractor, who had never worked in this region before, even though they were experienced, could adequately demonstrate their ability to execute an anchor under the conditions in South Africa. So it was very, very important. So we had 4 sacrificial anchors, and if you zone in, you could probably see them on the blocks there sticking out. And on 4 dress rehearsal anchors, sorry, 4 sacrificial anchors and 1 dress rehearsal anchor. And that was part of this program that the client decided to commit to. Now, these are very large anchors. They're full scale. And because of that, we had to fabricate them adjacent to the dam. Up in the left-hand corner, there's the left flank of the dam itself. So we had to fabricate these tendons in a very close proximity and then transport them to the installation location. The test anchors comprise 61 strands. Now, this would be challenging work for production anchors, but 61 strands was the option used to carry out these test anchors. And 4 of them were used sacrificially. Now, one of the issues that is often overlooked, one of the aspects that are often overlooked, when you're putting in a sacrificial anchor and you're looking to test it to its ultimate capacity, which is what we try to do, you have to isolate the bond zone of that anchor. Now, often this is overlooked, surprisingly, but what we don't want to do in situations like this is have the free length grout contribute to the resistance we're getting from the anchor, because that wouldn't give a realistic analysis later on when we're looking to back analyze what our ultimate bond stresses are that we can rely on in design. So what we elected to do is construct what we call an isolator or soft pack at the top of the bond length. And this polystyrene member was specially engineered, placed at the top of the bond length, so that when we stress the anchor, there's no contribution from the free length grout above it. So that when we get an ultimate condition or a maximum load, we know that it's the only thing generating that resistance is the bond length itself. So we can calculate that accurately. Here we have just a few images showing the drilling of the anchors in the Stilling Basin. For logistical reasons, it made sense to drill the anchors and install them, drill the boreholes first, and then place the thrust blocks over the case boreholes. We're dealing with large loads here, and the idea is you don't want punching forces going into the ground and complicating your subsequent analysis. So we had these 3 meter square thrust blocks actually constructed separately and then subsequently placed over the anchors. This is just a view of the tendon, fully fabricated here and wheeled into the test location on these special bogies. And then subsequently a tower crane lifting the test anchors into place. Remember, these are not production anchors. They're all sacrificial, but the client committed to this level of testing because they understood the benefits that will be derived from it. And once fully installed and grouted, the anchor was supported by a special test frame, left so the grout can gain full mechanical properties and then subjected to testing afterwards. Now, the testing process was quite interesting and very conventional, but what wasn't conventional is that we used a special software to allow us to analyze in real time the behavior of the anchors. And we use a software called Anchor Test, which was a cloud-based software based on iPad, which was very convenient because you don't really want to take laptops into a construction site because it's not terribly robust. But an iPad worked very well in these situations, and we're in real time able to analyze the behavior of the anchors. Essentially, in this software, we're able to input the basic characteristics, 61 strands, the free lengths, the bond lengths, the characteristics of that. Once the software understands that, and then we can now generate our load extension behavior. And in the case of BSA 281, it requires you to take an investigation test anchor through 8 cycles of loading and unloading until you reach an ultimate condition. And that's what we actually generated here. The software, as I said, was very successful and allowed authorized third parties to scrutinize the data, even though they weren't on site, because all the data was digitized and sent to the cloud for storage. So very, very useful tool in this test program. Now, I'm not going to delve into the numbers in massive detail, but this is just a summary of the back analyzed bond stresses that we generated from the site. The important thing to extract from this is that prior to this, the the specialist anchor contractor had not conducted investigation tests of this type before. They would simply rely on a desk study exercise, looking at the geotechnical parameters of the ground and estimate and calculate their bond lengths almost theoretically from that. So in actual fact, the theoretical bond lengths they calculated were up to 67% longer than the ones generated from these tests. And that's very significant because for the bond lengths generated were 6 meters, 7 meters, 8 meters, and 9 meters for the 49 strand, 61 strand, 80 strand, and 91 strand anchors respectively. So for the 91 strand anchors, it was unheard of that you could have bond lengths of just 9 meters when you're dealing with this type of loading. But the important thing here is that we carried out in situ testing on live full-scale anchors, which demonstrated the competence or the geotechnical capacity of the ground, so we could confidently use these values in our subsequent design. And that's what we did. So in addition to the sacrificial anchors I mentioned before, and I showed you a little red circle around it on the non-overspill crest, we also executed a dress rehearsal anchor. And the idea of this was that the contractor had to fully fabricate a full-scale production anchor with full corrosion protection around it, install it so we could critique his technique. We could iron out any issues, and this proved to be very, very, very useful. So this is a photograph showing this large anchor being winched into position along these bogies to its installation position on the crest of the dam. Remember, this is still a test anchor, and I put a little circle on there showing me inspecting that anchor while it's traveling to its location. Now, in order to home these into the boreholes drilled through the dam and into the underlying rock, you have to use special equipment. And this is what we call a dinosaur, which is a special rig with large pulleys on it. And it allows you to winch the tendon, which weighs a lot, into position and then safely lower it into its borehole within the dam and within the underlying rock. The stressing and testing is an important part of this exercise. And because the code of practice we used demanded that the anchors have to be cyclically loaded, we had to commission the world's largest hydraulic anchor stressing jack. And this was manufactured in Germany. I'm out of the 3 gentlemen there, I'm the one in the middle. And the gentleman on my left-hand side is actually 6'2". So it gives you a feeling for how big this jack is. Essentially 22 meganewton capacity. That's 4,946 kips. With a stroke of 1,000 millimeters. So this is the largest stressing jack ever commissioned for anchor technology that we know about. It was necessary because these anchors had to be cyclically loaded, and because of the size of the length of the free lengths, we had to have sufficient travel in that jack to facilitate the cyclic loading. Again, using anchor test software, we're able to subject this special dress rehearsal anchor, because it's not an ultimate test anchor now. It's installed in position, and we're subjecting it to what we call a suitability test, or in American speak, in US speak, what you would call a performance test, where simply we're subjecting it to 3 cycles of loading, extended observation periods, a little bit more rigorous than what you would call your proof test or our acceptance tests, a little bit more rigorous to show that the anchor's performing adequately. In this particular case, we also looked at what we call the apparent free length calculation, which is automatically generated in the software. And this really demonstrates that the anchor is acting elastically and that the load is transferred from the anchor head right through the ground adequately to the fixed anchor zone without any load caught up in friction in the free length, which typically can happen with long anchors. One thing I would say also is that provision was made in this system that if this anchor, dress rehearsal anchor, didn't perform adequately, then we had an adjacent position next to it to install a production anchor once all issues were ironed out. Luckily, in this case, it wasn't needed because it would perform satisfactorily. Now, the dress rehearsal anchor, as I said, it's not a sacrificial anchor where you don't need corrosion protection around it because the loads are very short term. We had to install a full corrosion protection system around this. Now, this is done by applying a corrugated plastic duct around the anchor tendon. And in BSA 281, you're permitted for permanent anchors to apply something called single protection or double protection. Both systems are valid in BSA in UK practice, in European practice. However, if you're applying a single protection, then you're required to test that protection in situ to guarantee that that protection has its full integrity. And that's what we had to do on this project. So once that protection system was installed, we had to water test it to show that there were no breaches in it. Then we installed the tendon inside it, water test it again. And once it's satisfactory, passes a water test, we are comforted that the full integrity of that system is in place and the single protection is satisfactory. With double protection, you don't need to do that. Now, we know historically that with anchors, the anchor head is the most vulnerable position for durability issues. And the majority of corrosion failures historically have occurred at the anchor head. So special provisions had to take place with this dress rehearsal anchor to ensure that the anchor head was adequately protected. Here, once the tendons are chopped off, this is 61 strands here, they were chopped off, the whole thing was then injected beneath the head, first of all, with a special wax, corrosion inhibiting wax, and this was subsequently placed around the chopped tendon elements so we can adequately protect them as well. Once that wax has gone off, the whole thing is encased in a galvanized cap, which is removable, so it can allow subsequent inspections of the anchor head during its service life. So this is the extent we had to go to ensure that the anchor heads were adequately protected, particularly because it's a very vulnerable zone of the whole anchor system. So how are cost savings affected by this initial testing? Well, one of the main features when you're dealing with this type of ground is that you have to waterproof the boreholes or grout-proof the boreholes. You have to ensure that the grout you place doesn't get washed out through fissures in the ground. So just refer you to this little schematic here to show you how the layout of everything is. We have the dam itself, the dam wall and the reservoir of water illustrated schematically. We have the borehole and the anchor tendon installed inside it. The phreatic surface, which is a natural water-bearing surface in there, and then the founding stratum, where the fixed anchor zone is located. And it's that founding stratum that we have to ensure that the grout is not washed out, so you can adequately retain mechanical properties of that grout when you're looking to stress it. So just cast your eyes on the diagram on the right-hand side, which is a schematic representation of the borehole. Now, the arrows show that there's a passage of water which can freely flow through the fissures and partings in the rock. And that can undermine the placement of primary grout. So if we simply placed our tendon in the borehole like that and grouted it up, then if we didn't do anything to ensure that that borehole was grout tight, then water could pass through, wash away some of that grout and undermine its integrity. So when we come to stress it, either the anchor tendon would start creeping excessively or simply pull out, which wouldn't be satisfactory. So what we have to do is waterproof that borehole by placing a grout initially in the borehole, re-drilling that, water testing it to ensure that it has it passes the criteria that are imposed. And if it passes that criteria, we can then safely place our tendon in that waterproof borehole, grout it up, knowing that the grout will actually stay in place. So we can stress it and it can give us the resistance that we desire. And what that essentially does is satisfy the condition in BSA 281, which is that the grouting is also to seal the ground immediately adjacent to the fixed anchor in order to limit the loss of grout. Very, very important. And because we carried out testing beforehand and optimize the size of those fixed anchors, we're able to ensure that they could be safely designed much shorter than anticipated, which limited the amount of pre-grouting we had to do and waterproof grouting. Now, in order to effectively waterproof a borehole, you sometimes have to go through several cycles of pre-grouting, re-drilling, water testing, etc. Several cycles to get that right, so you can pass your permeability criteria. So by shortening the boreholes and making sure that they can safely be shortened, the client saved tremendous amount of money on this particular aspect. So it's worth bearing in mind. And that was one of the benefits of the pre-production anchor testing. This is a down the hole camera which we placed, and it shows the effectiveness of the waterproof grouting, where on the left-hand side, you're seeing fissures, these round circles of fissures that are being grouted up and exposed after re-drilling and reaming out. And on the right-hand side, you're seeing the interface between the dam concrete structure and the underlying rock, and that interface is also grouted up. If that pre-grout wasn't in place, then the primary grout would simply just flow out and we'd lose the mechanical resistance we desire. So it shows the effectiveness of the pre-grouting program in filling all the voids. So the status of the anchors. I'm happy to say that before the contract was stopped, as I mentioned earlier in the introduction, in 2018, we had locked off 73 of the anchors, and these comprise 91, 80, 61, and 49 strand tendons. All of these were stressed and tested, and all of them successfully demonstrated conformance with BS 881 1989, which meant there were no failures. So that pre-testing program that we did, the optimization of the fixed anchor zones, even though they were shorter than what was theoretically predicted, satisfied the criteria and there were no failures. So that the testing program was effective and the in situ values that we used. In terms of the structure itself, I've picked views of the structure, typically looking upstream, as I mentioned before, so you can see the PKW in its finished form, as it were. But remember, we still have 10 anchors to stress, test, and instrument with load cells. And if you're very sharp-eyed, I'm not sure if you can see my cursor moving, but these are the tendons of some of those remaining anchors still sticking out pending the stressing and testing program to come. Another view of the drone as we flew the drone over, look an aerial view looking down at the PKW, which is a very simple configuration, but as I said, it increases the effective spillway length by a factor of 6 by adopting this configuration. And it's a low maintenance solution because it doesn't allow you don't need radial gates to control the flow using this configuration. And again, now looking downstream, these are just views of the dam looking downstream, beautiful area, but it shows the drama of the PKW in this view. So to some closing remarks. First of all, I'll say that the Hazelmere Dam has presented South Africa with a number of important world firsts. The first is that the largest capacity cyclically loaded anchors were installed. The capacity equaled the highest ever installed, but these are the largest capacity cyclically loaded anchors ever installed in the world. It's also saw the use of the largest capacity stressing equipment for anchors, and I showed you the photograph of the large bespoke stressing jack, 22 meganewton capacity. The highest PKW at 10 meters ever installed, the largest capacity sacrificial anchor program, and the first use of the real-time monitoring software anchor test on a dam for the storage of data and the real-time analysis of the performance of the anchors. So a number of world firsts that South Africa could be proud of. And I could add to that list by saying that we're also going to be introducing the largest capacity hydraulic pressure transducer annular load cells ever installed on an anchor as well. The second remark I'd like to make is that the project demonstrated the importance of implementing full-scale anchor trials for the optimization of the fixed anchor and the substantial cost savings that were generated from that in terms of reducing the amount of waterproof grouting that was actually employed on the project. I will also say that the waterproof grouting was effective in that the anchors installed satisfied the acceptance and suitability tests, or in US speak, performance and proof testing that was carried out. And finally, the use of the innovative data management software anchor test proved very, very effective in assessing the anchor performance with respect to the acceptance criteria stipulated in BS 881 1989. And with that, I'd like to thank you for your attention, and I'd welcome any questions.
Thank you very much for this presentation. Interesting presentation, and there are all kinds of questions that come up, and I'll leave some of those for the final Q&A. But two specific questions for your presentation. First one came in: what kind of chemical admixtures were used to waterproof the grout?
Right. Right. Well, excellent question. The primary grout was a 0.3 water cement ratio with additives added to that to increase the workability, particularly under conditions of heat and humidity. In terms of waterproof grouting, what was opted for was a neat cement grout with a lower water to cement ratio. A lot of thought went into that, but instead of using a 0.3 water cement ratio with additives for the primary grout, because we needed mechanical properties there, the waterproof grouting was only a sealing grout. Its purpose was purely to seal fissures. So the water cement ratio for that varied between 0.55 and 0.6, and that was adequate to seal the fissures, which is all it had to do. It didn't have to retain any mechanical properties. And typically that grout was left in place between 18 and 24 hours, re-drilled, so that you don't want to leave it too long, because if you re-drill it, you can deviate the drilling string and cause issues there. But you don't want to leave it too short a time in the borehole, because again, you could break your seal that you've just created. But essentially a neat cement grout was used for the waterproofing of the boreholes. Okay.
Other question came in was, are any anchors installed in the PKW zone?
Absolutely, absolutely. The PKW zone is a critical zone in terms of the whole stability of that structure. And there were anchors actually installed in the, if you look at the PKW configuration, although it's not obvious from the aerial shots, but certainly anchors were installed throughout all those blocks in there, a substantial, and in fact, 91 strand anchors were installed in there as well. So in fact, sorry, 91 strand anchors were installed adjacent to the PKW, but 80 strand anchors were installed within the PKW itself.
Okay. Thank you for that once again, and we'll have more questions about the logic of testing these kind of anchors and why it's not done more frequently. I would like to kind of work on that question with you and then try to explore it a little bit further, but we'll do that after our last presentation.
No
Cheryl,
problem
if you could move us back to the first presentation, because I think we have sorted out our technical problems with Patrick. But unfortunately, we now have to go back to where we were at the very beginning. The reason that, while she's doing it, let me explain the reason why I sequenced the presentations as they were, because what you heard being presented in the first presentation today was there was a technical problem and we need to figure out how to best resolve it. And by doing some testing, we came up with a very cost-effective solution. Well, Patrick has experienced a similar situation where during construction something went wrong and there were all kinds of options, but with a little bit of testing, they figured a solution that was much more cost effective and really helped the project along. So with that, Patrick, the floor is yours. Tell us about this project in the Netherlands.
All right, thank you very much, Gerald. Probably you can hear me now. Technical problems are solved on my side.
Yes, sir.
Thank you very much for your flexibility, and also to Dustin and Devon for filling in for me. So my presentation will take you to the Netherlands, tiny country in Western Europe, where Gerald and myself are at this very moment. Pilot testing on a tight schedule. Probably after hearing my presentation, you will tell me, Patrick, you should have arranged it in the other way around, and it will have saved you a lot of money, and even more people a lot of stress and sleepless nights. But probably next time we will do it in other order, and indeed increased testing will save money. I will give you a very brief introduction to my company, because we are far away. Yes, now we have control. I'm a board member of Van Hek Group. We are market leader in the Netherlands, but as you see the figures, we are only a smaller company compared to what you're used to worldwide, and in the US especially. We are a conglomerate of multiple piling companies, of which you see the names in the middle line. On the left-hand side, you see we also have our steel workshop where we do our welding, and we have our own engineering agency where we do our design, site engineering, technical support. And on the right-hand side, you see our business unit focused on international projects and on equipment trade. The project that I will tell you about is in the north of the Netherlands, a very small town called Bedum. That's where we construct a railway underpass in a meadow, actually. Our national strategy to increase road safety makes us replace level railway intersections by underpasses. And these underpasses obviously have to cross an existing railroad track, so it's made by stage construction during multiple train-free periods. And those train-free periods are then during a weekend, so no detours, just no trains for 24, 36 or even 72 hours. Those are replaced by coaches, so traveling during the period will take much longer. And well, the promise of the contractor is trains have to be back on track by the rush hour of Monday morning. And otherwise, well, they will get huge claims for logistics problems, more coaches, and loss of time and turnover by companies who depend on it. This is what a typical level railway intersection can look like in the Netherlands. And this is what we would like to, well, to make in future. So what you also see is, you see that the road is separated from the bicycle lane, so safety increases much in this case. The rail deck foundation that you just saw on the artist impression is bearing on 2 abutments with 8 screw injection piles with a length of 75 feet each, and 2 intermediate piers with 12 screw injection piles each to even 101 feet. For those who have never heard of this screw injection pile system, it's quite common in the Netherlands and Germany. In this case, we use a steel tube with a well-done lost drill head, but we also make these piles with a temporary casing, which is extracted after pouring concrete in situ. But in this case, a lost steel casing with a diameter of 30 inches and a drill head of even 38 inches. We use grout injection during installation for as lubricant during installation and to improve the bearing capacity of the steel casing. The soil conditions in this particular project are quite different from what we used to in the Netherlands. In the Netherlands, most construction projects are in the west of the country, close to the sea, actually in one big river delta, where we have very soft clay, the Holocene layer on a Pleistocene sand layer. Pleistocene sand layer offers bearing capacity, and that's what all the engineers know. They know how to deal with it, and they know how piles perform in that particular layer. However, in this area, when you look at the cone penetration test diagram, you see from 13 meters below surface, you see over consolidated stiff clay. We know it as pot clay. This gives a whole other approach to bearing capacity, but in the Pleistocene sand layer, which I mentioned, we look at end bearing of piles and high friction ratios close to the pile tip. And in this particular case, well, we forget about end bearing, and we all have to get this bearing capacity from shaft friction, but we don't know so much about this pot clay bearing capacity. So we have, well, a good couple of tests, but they are all very old. Statistically, they are, well, much away from each other. So we have kind of safe values in our code, and it's not common practice to do pile tests in projects in the Netherlands. We are very much dependent on our design methodology based on cone penetration tests. Well, also these pile lengths, which I presented, 31 meter, it's rather long for what we are used to. So luckily for this project, we had some training before we had to install piles during those train-free periods. If you look at this design drawing more carefully, you see a safety zone A in the middle, which I now point out with the cursor. You see a small safety zone B. And you see that there are even some piles outside of these safety zones. Those 20 piles inside safety zone A are in the middle of the rail tracks, so they can only be installed during a period where there are no trains and when actually the rails is taken out. And after this period, the rails will be placed back in order to let the trains run. During one train-free period, we install the piles. Tracks are brought back in place. After the train-free period, the train will be back in service, and in the next train-free period, rail deck will be placed. And after this, well, the new rail tracks are in place, but the underpass will be excavated underneath the new rail deck. So what I said, some training. The 20 piles which are outside of the safety zone, and actually 12 are outside of all safety zones, can be installed with the tracks in service. 8 piles which are in safety zone B can be installed with some extra safety measures, but with the trains in service. Which meant that we could test our performance of installation before we were on this tight schedule of a train-free period. Well, this is when we first found out test piles would have been a good investment, because some of those training piles took over 6 hours. Well, we only budgeted for 2 hours. Yeah, that's a pity as a contractor. However, that's your own money, but not making it in a train-free period, that's a real problem. The probable cause of these disappointing installation results were the limited effect of the cement grout in clay. Normally we use cement grout in sandy layers, and it helps us as a lubricant to screw those piles to the design depth. And the same case for these lost drill heads which you just saw. Those seem to be less effective in clay. Another factor was because these piles with those 30-inch tubes and 37-inch drill heads tend to start floating when they reach a certain critical depth. This was not looked at by the engineers beforehand. It's not that the piles come out, but at a certain moment the uplifting force tends to be higher than the pull down force of the piling rig, so you don't go anywhere. So normally you use a grout with a low water binder ratio in order to have a high cement content, which gives your mixed in place mortar that you create during installation some strength. You take it as an interface with actually, so you can take into account a larger diameter in your design calculations. In this particular case, the grout was only working against us during installation, and even since the water could not drain properly in the clay, we were only pushing the pile up extra next to the floating problem after reaching critical depth. The limited effect of the drill head teeth in clay. Well, we found out during installation that the clay was clogging underneath the drill head between the teeth, and well, we get a bulb of clay underneath this drill head, and the teeth were not effective anymore. And normally in sands, they just cut through the sands, spread the grout around. Well, and we have a very efficient installation process. Pile buoyancy, this could have been foreseen. Normally with smaller pile diameters, the weight per area is higher, and you have your rig's pull down force, which is much higher than the buoyancy of the pile. What we normally do when we have large diameters steel tubes with a closed toe, we will fill this with concrete during installation. However, in most cases, we don't have reinforcement over the full length of the pile, so you fill it until the end of your reinforcement cage, so you can place the reinforcement cage only after installation. But in this particular case, we had reinforcement cages over the full length. So in order to fill these piles with concrete during installation, the cages had to be placed also during or even before installation. Because we were looking at pile installation during a train-free period with a cycle time of only 2 hours per pile, we later placed these reinforcement cages in the steel workshops where the steel tubes were assembled. Well, the measures taken to improve installation cycle time in the second training were a decrease of cement content in grout. We discussed it with our client, with the engineers, and together we decided to add some bentonite to the grout, but still with a large cement content. As I just said, placement of the rebar cages in the welding workshop, so no extra works on site. And pouring of concrete we did with concrete pump truck after 10 to 12 meters of driving, so before reaching the critical depth for buoyancy. Well, this is what it looked like, the left-hand picture just before start of the project, and at the right-hand picture, the tracks are taken away, and well, nobody has an idea that there has ever been a railroad track. But on Monday morning, it looks again more like the left-hand picture. Well, all piles were installed successfully in the available time frame. So the trains were running on Monday morning along the tracks that were brought back in place, just on the normal ballast bed that was in place before we placed the piles. So the piles are not yet in function, but they are there for the next construction stage. Well, the next construction stage would be within about 2.5 months. But after evaluation of this first train-free period, we found out when checking the piling logs that there was high water usage during pile installation, low cement usage, bentonite. Well, we use much more, kind of in line with liters of water. Grout density at the start was too low. Grout density halfway the installation process was too low. And finally, the grout density at final depth of pile installation was okay. Normally during installation of these type of piles, you have your grout backflow. So probably while reaching design depth, all the grout with low density is already displaced, replaced by grout with a higher density. So with the well, agreed cement content. However, you cannot prove that there is not either a bentonite interface on your steel tube or between the soil profile and your grouted annulus around the pile. So that was a problem. We had a crew who optimized the drill mud during the installation process and well, managed to install those piles on time, but we obviously did not do what we promised. So we discovered at the end of August 2021 that we had this issue. The next train-free period would be on October 22nd, 2021. So we had 2.5 months to go to prove the piles had the required bearing capacity. Normally, when you have some piles that are not trusted, you can test them, and in that way prove they are okay. In this case, we only had the installation logs that showed we did not do what we agreed. Well, nobody with too much experience with this type of soil, also no consulting engineers, external engineers or other contractors. Piles were under the railway track, so we could not test them. So we had 2.5 months actually to install sacrificial model piles, to do the testing that we should have done beforehand, well, before the next train-free period. Yeah, what was above our heads? Scenario 1, the next train-free period could not be used to place the deck. So you get a change of design, you get a modification of the foundation. If you get a modification of the foundation, obviously more piles, you get modifications to the deck. 2 extra train-free periods are required. 1 to place the extra piles, and one for the deck placement. And you have potential claims between 500,000 euros, so about 550 in dollars, and 1.5 million in euros. You have a lot of reputational damage in the industry. Scenario number 2 was even worse, but actually we were the ones who pulled the brake to not go there, because if our client accepted the piles as they were on a theoretical motivation, we would have risked unacceptable settlement after commissioning of the underpass. Well, risk of severe delay damage, taking the train tracks out of service, potential claims certainly above 1.5 million euros. Severe reputational damage, not only in the industry, and probably an 8 o'clock news item. 2.5 months until the next train-free periods. So it took us 4 weeks, or actually we took 4 weeks for the test setup design, additional soil investigation on the place that was designated for the test piles, immediate installation of test piles, which is then a setup period to get there, to develop the shaft friction during 1 month. After installation of the test piles, together with our client, the contractor, we informed the railway authorities, local authorities, and then we agreed on the test result interpretation protocol. There actually was no time to inform them before, because we knew if we would get into a discussion about this setup, we would for sure not make it in 2.5 months. After 2.5 months, we had 2 weeks for testing and interpretation of the results, and 1 week left. Well, you see a picture of the test setup. We took scaled piles, so 20-22 inches, with a crowd composition as we found back in the pile logs from the piles installed during the train-free period. So with low cement, much more bentonite, much more water. We had a test setup with 325 metric tons in Kentlet's capacity. And a pile failure load, we found out, was about 200 metric tons. Why then a 325 metric ton setup? Because we could not agree on the actual pile bearing capacity, taking into account all the layers that are there, but do not contribute to the bearing capacity during the service, but who will definitely interfere your testing. Well, we needed this extra week badly because of strain gauge interpretation. Short story, you can never have enough strain gauges because some went out of service. There was some discussion about the trajectories below the strain gauges that could have divided better if we used more strain gauges. In the end, we found a safe best estimate of the load-bearing capacity of the pot clay layer, where it was all about, and we ended up with an acceptable less than 8% underperformance in relation to the design values that were earlier chosen. We had about 8% left in our safety factors, so we saved the day. Then I want to show you this video. because this is what happened during the weekend from Friday 22 October until Monday morning 25th of October. You see on the left hand side, which I point now out with the cursor, the new railway deck. The excavators already took out the tracks and the whole railroad. The rail deck is pushed into place. And the test train runs. Well, thank you very much for your attention. Feel free to ask me any question.
Thanks, Patrick. Thanks for your presentation. Question that obviously comes up after this experience that you've had. What are you going to do differently with jobs in the future? Yeah, because in Holland, of course, as you already mentioned, load testing is not all that common. You basically do your design and then you install it and you hope that everything goes well. Has this project changed your approach, changed your outlook on how you would do other projects like this?
From a risk management point of view, we would in this case always advise our clients to do the testing, because you heard in my presentation, we did not do what we agreed on, but we were also testing. We found out during the testing because nobody knew exactly what those piles were up to in this clay, and we did not know, and the experience for installation was not there. So there are many reasons why we should have done these pile tests. Now we did pile tests and we made internally some 300,000 euros in costs. Probably when we would have put this in our budget beforehand, it would only have cost us 150,000 euros.
Okay. Carol, if you could turn off your screen, and if I can ask all the panelists then to turn on their video, their webcam, so that at least the audience can see us rather than looking at now a screen that says Q&A. Would be helpful. Let me start with a question to Devon. You described in your presentation the need for this testing, and it made a tremendous difference. To me, and when I saw your presentation first, it was kind of, yeah, of course, when you have anchors like this, you should do testing. At the same time, though, it's not common practice in the industry, it seems. Why is it, and then what can we do to really convey this message to the industry? And there's a reason why I'm asking you that, to give you a little bit of background. We've had this series of It's Money webinars now for a long time, and lots of things have come up. Iterative cases on different pile foundations. This is the first one on anchors. So I want to dig a little bit deeper when it comes to anchors to figure out what we can do to convey that message that we have probably been able to convey to other types of foundation or soil investigation methods in the past.
Thanks for the question, Gerald. The first thing I'll say is that one thing that distinguishes anchors from other types of geotechnical technology is that testing is a mandatory requirement for all anchors before they're brought into production. So all anchors have to be mandatorily tested. What we're talking about here is a commitment of a client to do pre-production testing before the main production anchor starts. And usually the issue is one of cost, primarily, and educating the individuals or the asset owners to know that an upfront spend can mitigate risk in the long term and create cost savings in the long term. It's that education process. Now, what I find in my experience is that when it comes to structures like dams, where the consequences of failure are very, very high, the discussions on testing are quite easy to have because asset owners tend to be more risk averse. They because it's high consequences of failure. If a dam fails, and with this, litigious age that we're in, the consequences are massive. So the convincing them isn't that hard. When it comes to lower tier structures, you're dealing with where the consequence of failure are less, then cost becomes a critical issue, and people start relying on previous experience and that sort of thing to get the contracts going so they can avoid the initial costs associated with testing. So to answer your question, I find that more and more convincing clients to do investigation tests or pre-performance tests isn't that difficult when it comes to dams, purely because of the consequences of failure. So more and more you're finding it is becoming more and more common. Perhaps not necessarily to the scale that I described, because this is actually the biggest in the world, but it's because South Africa had never experienced this type of technology. So they were very risk averse and they wanted complete assurances. That's why we had to do a dress rehearsal anchor. That's why we had to do those sacrificial anchors first. Obviously, where experience comes into play, you have an experienced contractor who knows the ground, who knows the region. You can modify the extent of that testing to reflect the experience of the contractor in that particular ground form. But where there's no experience, testing is a must if you want to mitigate risks. So the simple answer is that I'm finding the argument a lot more easy to have, the discussion, when it comes to large structures where the consequences of failure are high.
But what about if you do your testing during the design stage or upfront, you may also optimize your anchors as well and then save cost again.
Correct.
Correct. Then it is not only a matter of minimizing your risk, but also actually the cost of the anchors, and therefore still save money. Sure. Is that something that is generally recognized, or are people saying, nah, don't do that, let's just install whatever we feel based on our experience? Yeah, it's just doable. And then of course you never know that you could have done something more cost effective, because you only prove that the anchors are adequate, but not necessarily how you could have optimized your design.
Yeah, it's a debate I have all the time. More and more, you even find this with Eurocodes. There's now an inclination towards using theoretical derivations and applying increased partial factors to allow for the fact that you may not have tested in the field. So it's compensated that way. And there's a tendency to move that way, but I'm having the debate because I feel that where anchors are concerned, they're highly sensitive to the construction processes, highly sensitive to that. So the way to get around it is not by relying on increasing safety factors or partial factors, but by looking at in situ testing. Because it's so sensitive to the construction processes influence what happens in terms of the results you get from the field. So you need the contractor who's installing the anchors to conduct those tests. That way you can get a realistic impression of the parameters you can use in design ultimately. And this is a debate I'm having all the time to convince clients that this is the way to go because of that sensitivity to the construction process.
Well, I'm sure you are not the only one who has the discussion. Dustin, going to you, within Keller, how do you see the same issue? And then what is your experience in the last couple of years? Are we getting closer to that people are saying, yeah, let's do more testing and optimize the design? Or are we still where we were, say, 5 years ago?
Yeah, no, that's a great question. I think Devon hit it right on the head on those structures that we're building that are high risk averse. I think we're getting closer. But those ones that are less risk averse, where the risk is not as dangerous or as big of an issue. I think I don't know that we've made it there yet. I think part of the issue is, what I see is that contractors, clients, everyone, they're in such a hurry to get everything done. The time to get this upfront testing done, by the time they get to getting that contractor, whatever that Devon, getting the right contractor out there, the design phase is already done and it's been permitted and it's time to get to work, right? They don't have time to spend weeks or whatever it is to get out there and do this extra testing. We find the same thing when it comes to geotechs, doing additional borings or anything like that. The time to do those is passed by the time they're ready to sign them up. Design's been done, they're ready to go into production.
Right.
Scheduled for quick.
Obviously, you're part of Keller, an international organization. I'm sure you talk to your colleagues in other parts of the Keller organization outside North America. Do you think that there is a difference in different areas of the world when it comes to the views on testing, or is it pretty much that your experience here in the States is kind of the same in the other parts of the Keller organization?
That's a good question. I don't know that I can, my conversations with people outside of North America have not been so much on the testing. So I don't know if I can answer that one. I'll leave it more to Patrick or Devon to answer those areas out there. But
well, Patrick, going to you, you're part of an international organization as well. Probably not as in the same scale as you have in with Keller around the world, but do you see that there's a regional difference or a difference in the different countries when it comes to the views on testing beforehand to optimize the design, or do you say basically the experience is all the same?
Well, no, for sure, because I know in Germany and probably Devon will confirm in UK, it's common practice to do pilot tests as part of the project, as part of the pilot contract. And our experience in the Netherlands is, well, as I just said, it's not common practice to do pilot tests. However, anchor testing, as Devon says, each anchor will have its own tests, whether it be a suitability test or a short test. All anchors are tested because otherwise you're out of competition because you have to make longer anchors. But for common bearing piles, actually on a project as a deep foundation subcontractor, we are first on site, however, last in the procurement process. So this time that is required for installing test piles is just not there in a normal process. And on such a tight time schedules, clients don't want to hear about it, because what if testing reveals something they don't want to know? Then they know it, and then it's not for the insurance company, but it's for them to solve. Very strange approach, in my opinion. So we are dealing with that, and sometimes we are successful. And we have a lot to share with our clients, because in this particular project, which I presented, well, after testing, we would have said we need more time, so our budgeted price will become higher. However, in some projects, we managed to reduce number of piles. We see we have a better performance during installation. And that's what we would like to share, because it's also for us, it's risk mitigation. We have a better feeling of what we are going to do when we are on site, and how we will end our project. So yeah, to be short, in the Netherlands, it's probably more like North America, but in surrounding countries and farther away from home, I know testing is common practice.
Okay. Devon, anything that you would like to add to that?
Yes, certainly. I mean, interesting point Patrick mentioned there, and that I talked about earlier on, about the fact that it's a mandatory part of the process to test all anchors. Now, fundamentally, the reason for that is that the view has been in the industry that the integrity of in situ placed grout can never be guaranteed. Once you bore a borehole and you place grout in it at depth, you can never guarantee its integrity. So you don't want to wait until you're making demands, the structure's making demands on that anchor till it suddenly shows itself to be effective. So that's why we mandatorily test all anchors before they're brought into service as a routine part of the process, because you can't guarantee the integrity of grout placed in situ. The big question here is, will someone spend money up front doing pre-performance tests? That's the key thing. Or do you rely simply on the experience of the practitioner? And like I said before, without wanting to repeat myself, because the whole process of anchoring, you're dealing with members which are subjected to tensile forces, and tension is very unforgiving in nature. Compression is a lot more forgiving. And because you're subjecting it to tension, it's very reliant on the quality of the construction. And if the construction is bad, then the thing tends to fail. If the construction's good, then it tends to pass. So I'm inclined to encourage asset owners to say, look, get testing done up front, particularly with high risk structures.
Right. Before we go on with this discussion, because I have some follow-up questions on that. One question came in about your presentation, Devon, that said, did you perform any earthquake analysis for vulnerability consequences on the ground anchor structure behavior?
Interesting question. It just so happens that South Africa is not an earthquake-prone zone. So it wasn't a requirement of the design process to carry out earthquake analysis and go to that expense, because earthquakes are very uncommon in South Africa. But the question raises an interesting point, because there's different schools of thought when it comes to dealing with anchors and earthquakes. Some people take the view that if you can predict the amplitude of the earthquake in terms of overall movements, you could try to lock the anchor down, and so you can inhibit that movement. Another school of thought is said, don't try to fight what nature's doing. And if you want to lock your anchor off, which is the lock-off load is primarily there to inhibit deformations, you can take the attitude of adopting what they call a soft lock-off. So rather than locking off with a heavy working load, you can apply a reduced working load, so that as the structure moves and deforms, the working load is acquired during the service life. And that's another way of accommodating excessive deformations as well. But it's a complex area, earthquake analysis and dynamic analysis where anchors are concerned. Ultimately, the anchor as a member itself doesn't alter in design. What you can alter is the amount of load you put on it to accommodate the feature you're trying to combat. But it wasn't a relevant aspect for South Africa.
Okay, fair enough. Coming back to what we were about a few minutes ago, when I asked all of you to participate in this webinar series, the answer was, yeah, great thing, more than happy to do that. Let's talk about testing that saves money. And it's the same message that I get from all the people that I've invited for this webinar series. At the same time, when it comes to owners, when it comes to lots of projects, there's still this reluctance to actually implement this concept of increased testing saves money. So that's why pretty much every single webinar, I ask all the panelists this fundamental question. What do we need to do as an industry to convince the non-believers or the people that are not yet on board that this makes sense? Any suggestions, any things that we can really do within DFI or within the industry in general to really drive that message home? Any suggestions that you have in that area? Any of you?
Well,
Dustin, let's start with you. Okay, Patrick, go ahead.
Sorry. I actually had this discussion just a couple of months ago in the Netherlands, and a generally shared conclusion was, if we connect it to sustainability, there certainly is another reason for clients to implement testing. Because if we can optimize design, it will help, for example, in our BREEAM certification or in the carbon footprint of the structure to be built. Because if we cannot wake them up by saying it's risk mitigation, well, then maybe that's a way.
Okay.
Interesting point. I think it's all down to education of whatever form that takes. It's about exposing the asset owners, the clients, to educating them on simply educating them on the benefits. You know, if people don't realize that upfront spending can derive benefits later on, then they won't adopt it. So seminars, you know, all this kind of stuff is so useful in getting the message across, and it's about sharing that knowledge and sadly pointing to people towards litigation circumstances and failures where testing wasn't carried out adequately, and that resulted from that. So almost we can frighten them into action as well.
Right. Dustin, anything you would like to add in that area?
Yeah, I mean, I think Patrick hit a great point there with sustainability. I think that's a big thing that's coming around. We see it a lot here in North America. It's a big push right now. And then hitting on Devon's point, I think Patrick brought it up before, as contractors on our end, we're the last ones procured. So our big push lately has been working with the architects, structural geotechs, informing them of the benefits that can be done from additional testing. So they're the first ones in front of the asset holders, the owners of these projects, so they can bring that up in the beginning and hopefully get the process rolling early.
They indeed are the ones who have to, well, scare the owners.
Whatever it takes, Patrick, whatever it takes.
Well, maybe it's a good note to end it on as chair of the DFI Sustainability Committee. Maybe we need to start joining forces here and then drive the sustainability aspects and to really promote this concept of increased testing saves money as well, and make it a joint effort between Testing and Evaluation Committee and the Sustainability Committee. With that, I want to thank you very much for giving your presentations. Really appreciate your cooperation, interesting case studies, and especially when it comes to Devon, you were the first one to give a presentation on ground anchors. So another first on this project. You gave all kinds of firsts on this project. Well, now it's also the first project that was covered in its money when it came to ground anchors. So there we go. But seriously, thank you very much for participating. Thank you for giving your presentations. And for the audience, thank you very much for logging on, for participating in this webinar series, because in the end, it is not for us. It's not for the people that give the presentations, because we are convinced that increased testing does save money. It's just trying to get that message out to owners, to contractors, to project developers, that this makes sense. And hopefully you've heard 3 more illustrations of that concept, and maybe that will change the industry. So with that, thank you very much. I know that I won't ask Carol to she puts the slides on and back again. So she knew what I was going to do. This webinar series, of course, takes place every first Wednesday on even months. So the next webinar will be on the 1st of June, and then on the 3rd of August. And I hope to see you all back there. And in the meantime, stay safe, and I look forward to seeing you in the future. Oh, I forgot one thing. You will get PDHs for this webinar, and normally it says there that the certificates will be out in about 3 months, but in reality, or 3 weeks, but in reality, they will go out a lot sooner. DFI staff is very efficient on that. And if you have any questions about this whole thing, you can see there that you can send it to techactivities@dfi.org to get any questions about this communicated to us. But also if you have any suggestions on projects that you would like to see covered on here, or even make a presentation yourself, please feel free to reach out to us. And with that, I want to thank you for being here, and I look forward to seeing you in the future. Thank you very much.
Thank you very much, Gerald.
Thank you.